today we're going to continue with the same section and study hydrostatic force and pressure. So, yeah, this is going to be the topic of today's class. 2 more weeks of classes, but so many applications to physics, engineering, biology, economics, integral calculus, and lots of questions. Okay, so when we discuss about hydrostatic pressure, we only take into account the pressure of the fluid at rest. So in other words, we are diving somewhere underwater, and we feel a pressure from the water, which is basically kind of like the gravitational force of the water on top of us. And the hydrostatic pressure is only the pressure of the fluid at rest. So in other words, we don't count any kinetic motion of the water. So we don't see waves breaking or stuff like that. So, and the definition, this is pressure exerted by a fluid at rest. And it has a very clean formula, so the pressure is going to be the density of the fluid times the constant of gravitational acceleration times the depth. So the quantities over here as are density of the fluid in most applications we only deal with water, so it's going to be like 1,000 kilograms per cubic meters. G is the constant of gravitational acceleration. So it's roughly 9.8 meters per second squared. And these are constants, and the only thing that changes is y. So y is the depth. So you see from here that the hydrostatic pressure is just proportional to the depth. So it's going to increase as the depth increases. And also the hydrostatic pressure is constant along all directions. So if you're a coin submerged underwater, you'd feel hydrostatic pressure which is constant in all directions. Okay, so that's one definition for the hydrostatic pressure. And another way to think of the hydrostatic pressure is as a function of the force exerted by gravity over the area So the pressure is something like the force divided by the area. So F is the hydrostatic force. And it's like a gravitational force of the water on top, so it's just like the weight of the water. And A is the area of the object that is submerged underwater. And usually this formula right here, you see it presented in a different way. You see it as the hydrostatic force equal to the hydrostatic pressure times the area. Because technically, first we compute the hydrostatic pressure, which only depends on the depth, and then we compute the hydrostatic force, which depends on the pressure, but also on the shape of the object that is submerged underwater. Now, the formula over here is very nice, but it also holds in very special circumstances. So, to apply the formula over here, we need to assume that all points on an object which is submerged underwater are at the same depth. So, in other words, a situation in which the formula over here holds true is when you have some sort of thin plate that is submerged horizontally underwater. So every point over here is going to experience the same pressure or the same force coming from the water on top. So this is like this plate submerged horizontally. And the formula over here works because every point on the plate over here is submerged at the same depth. So it has the same pressure from the water on top. Now, in most applications that we will do, this will not be the case, so we will not be computing the pressure on the bottom of something or on a thin plate which is submerged horizontally. We will be computing the hydrostatic force of the water which hits against the dam, so something which is going to be submerged vertically or tilted or whatever, and because not all points sit at the same depth, it means that the pressure is going to be very different along the object. So on the top, if, I don't know, the water comes like that, then whatever is above the water has basically no influence from the water whatsoever. There is no hydrostatic pressure over here. At the top of the fluid, the hydrostatic pressure is zero, but as you go down towards the bottom of the object, the hydrostatic pressure is going to increase, and the force will increase as well. So we can no longer apply the formula over here for situations like this. Okay, so let me finish off this brief introduction by telling you what the measurement units are in the standard international units of measurements. So you already know that the force is measured in newtons, so the standard measurement for the force is the newton. And for the pressure, we can see that the newton per square meter from here, but there is also another convention for this one, which is the Pascal. So the SI unit for pressure is a Pascal. And this is abbreviated like 1 PA, and this is equal to 1 Newton per square. Okay, so this is not a course in physics, so I don't want to stress too much on these ones. So after this brief introduction, I think we'll just proceed with some examples. I'll first do an example with something which is horizontally underwater, even though it's not very representative to the kind of applications that we'll do later on, and then I'll proceed to this kind of situation. Any questions so far? Are we good? You all know about hydrostatic pressure. You've dived underwater. So okay, so let's consider this example. You've got a cylindrical container which is going to be filled with two liquids. So over here we've got water, and on top we have some oil. Some dimensions over here 2.4 meters. From here to here 1.5 meters. And the diameter of the bottom is 3, so like the radius is just 1.5. So we've got a container of this sort which is partially filled with water and oil. You know that oil is usually less dense than water, so it lifts on top. The density of the oil is 900 kilograms per cubic meter, and the density of the water is 1,000 kilograms per cubic meter. And the problem is asking, what is the hydrostatic pressure and the hydrostatic force at the bottom of the recipient, of the cylinder of the fluid. Asking for the hydrostatic force and pressure of a thing which is horizontal. It means that basically every point on the surface over here is going to experience the same action from the liquid on top. So basically to compute the hydrostatic pressure, we just need to see what is the depth, what is the height of the fluid on top if you want. And to compute the force, all we need to do is to multiply the pressure by the area of the bottom. So let's do just that. You'll see that the example over here is quite easy, but the computations are not so easy. So those numbers over there are not really very well chosen, and I'll help you with the final computations because I don't want to lose too much time with the example. So basically, to compute the pressure, we need to add two things. There is a pressure coming from the oil, and there is a pressure coming from the water. So let's account for both of those, as seen from the bottom of the cylinder. So what is the pressure, the water pressure? Well, we have a formula for this. So if you are somewhere on the top of the cylinder, the pressure coming from the water on top is going to be the density of the water times the constant of gravitational acceleration times the height of the water on top. So that would be 1.5 meters. So I'm just going to write over here 100. And for the oil, we're going to have a similar thing. And to compute the total pressure, all we need to do is to add the two together. Okay, so let's do some computations over here. So the density of water is 1,000 kilograms per cubic meter. The constant of gravitational acceleration is 9.8 meters per second squared. And the height of the water on top is going to be 1.5 meters. And because all measurement units are expressed in standard measurement units, we're going to get the final answer expressed in pascals. And the answer is something like 14,700 pascals, which is just 14.7 kilopascals. Okay, so we do the same for the oil. The density of the oil is now 900 kilogram per cubic meters. Constant of gravitational acceleration is the same. And the level of oil is 2.4 meters. And this gives 58,168 pascals. I told you that the computations are not the most straightforward. It's what happens with examples chosen from the book, I guess. In any case, so modulo some arithmetic over here, modulo some multiplication, this is what we get. So the total pressure on the bottom is going to be 14.7 plus 21.1, 21.2, and this is going to give us 35.9 kilopascals. Okay, so you see that the pressure at the bottom of the container doesn't really see the shape of the bottom of the container. So it only takes into account the level of the water or of the oil, which is on top of the bottom. But the formula over here never takes into account the actual shape of the bottom. This is something that we are going to have to quantify whenever we compute the hydrostatic force. So having computed the pressure, now the hydrostatic force is the same on every point of the bottom because this is submerged at the same horizontal level. So now the force is just going to be the pressure times the area of the bottom. The pressure, we've computed it, and you see that the area of the bottom is just the area of what is with radius 1.5 meters. So its area is just going to be like 5 times the radius squared. So pressure is 35.9. And the area over here is 5 times 1.5 squared. And because the pressure was expressed in kilopascals and the area was expressed in square meters, we will get the final answer expressed in kilonewtons. So if we are very thorough and I wanted to get some measurement unit, the appropriate measurement unit would be the kilonewton. Okay, and what's the computation going to result in? 253.8 kilonewtons. Okay, so I didn't want to do computation because they're not very easy. So sorry for just putting them on the board, but the final answer is not so relevant as the process itself. Okay, so in this example, basically we were able to just use the standard formulas for hydrostatic pressure and force because we had something which was horizontally underwater. Every point on here had the same pressure, so we are just able to use the standard formulas with no integration whatsoever. So, if you've understood this basic example, I would like to move on to to something which is going to be a little bit more tricky, and it's going to involve things which are submerged vertically underneath. Any questions so far? You're good so far, right? I haven't lost you on the first example. More important is just to add them at the end. To know that the force is measured in newtons, that the pressure is measured in pascals, so it's not so important to imagine liters per second squared or something. Okay, so let's consider the following application. You've got some object in the shape of a triangle, which is submerged vertically underwater, with the top at the surface of the water. So this is a right triangle over here. The vertical side has 3 meters, the horizontal side has 2 meters. And let's put some words over here. So calculate the hydrostatic force on one side of a plate in the shape of a right triangle of height 3 meters and base 2 meters. Which is submerged vertically underwater. Now, if I write over here, can you still see, or do I need to write further up? Is this line still good? And with the upper vertex located at the surface of the water. Let me not write that, you see that the vertex. Okay, so we've got to compute this, and as I kept mentioning, it's not okay for us to use the formula where we say the force is the pressure times the area, because the pressure is not constant along the object which is submerged underwater. So, at the upper vertex, the pressure is going to be 0 because it sits exactly at the surface of the water. As you go down, the pressure is going to increase. And because it's not going to be constant along the object, we cannot just go ahead and say the hydrostatic force is the pressure times the area of the object. What pressure? Is it 0 at the top? Is it more? No, that's not a good formula. So the idea over here would be just kind of try to divide the object in question into smaller objects that sit at the same level. So the idea would be to consider, instead of the total hydrostatic force, just the hydrostatic force on some thin horizontal strip of the object. And this thin horizontal strip is going to have some negligible height, delta y, that we can assume to be small enough so that the pressure along the object over here is basically constant. So for this kind of thing, we're going to be able to use our standard formula, which says hydrostatic force is the pressure times the area, and then we will need to somehow total the hydrostatic forces along these thin strips, and totaling those hydrostatic forces, adding them together, is something that we know how to do using integers. Okay, so let's put more content to the problem over here. Let's first introduce a vertical coordinate from the surface of the water tower, which just measures the depth. So plus y is just going to measure the depth of the water. And first, let's see what the hydrostatic pressure is at depth y. The problem is not specifically asking for it, but we will need it anyway when we compute the hydrostatic force. Now we have a formula for it. This is P of y, which is equal to the density of the liquid times the constant of gravitational acceleration times the depth. So this is just rho gy. So in other words, if we are at depth y, anywhere on the surface of the triangle, but at depth y, we are going to experience a pressure which is just rho gy. And again, the pressure doesn't really see the shape of the object, so it's just rho gy. Okay, now let's postpone the actual computations at the moment. So let's just keep it as rho gy for the time being. And let's try to estimate the hydrostatic force. On the thin strip that I've drawn over there, let's say that the width is going to be W of y, and height delta y, which is close to 0 but not yet 0, so I'm just going to put over here a tiny sign to keep in mind that this is really, really small, but not 0. And the thin strip sits at depth y. The height over here, delta y. And the distance from the top, so if we were to take this side, it's just anyway, this line will come. Okay, so now the assumption on the strip over here is that all points sit roughly at the same depth from the surface. It means that for the thin strip only, we get to apply the formula which says that the hydrostatic force is the pressure times the area of the thin strip. Now, this thin strip is just a rectangle whose width is W of y and height delta y. So naturally, we can easily compute the area by just multiplying the two lengths. So let's write the formula for the hydrostatic force. The hydrostatic force is just going to be the pressure times the area. And now, because this varies with the depth, I'm going to write them as functions. Depth so what is the pressure then? The pressure is rho gy from before. And what is the area? Well, as we said, we've got a rectangle whose width is W of y and whose height is delta y. So over here, the area is just W of y times delta y. Okay? Let me put it over here so you don't forget it. A of y is W of y. Okay, so far so good. In the formula over here, it looks like we know every quantity. Rho g are just constants. Y is the depth. delta y is something which is going to turn into something very small. It's going to be the dy of our final integral. And the only thing that requires further computation is the width w of y, which changes with the depth. Because you see that over here we've got thinner rectangles, as we go to the bottom, our rectangles are going to increase in width. So the only thing that requires some computation is the width w of y, and there is a technique which is kind of standard for doing so, that of similar triangles. So if you have a picture like the one I'm just about to draw, after I place 1 kilometer square from backward, is something like this. Suppose you have a triangle. This is divided into two similar triangles. Let's label them A, B, C, D, E. Now, if these triangles are similar, in the sense that, they have the same angles, so this angle is the same as this angle, then the length of the sides which oppose the equal angles is proportional. You already know that, but I feel obliged to write it. You've probably used it many, many times. So this is the way in which you do things. And what are the similar triangles over here? Well, one triangle has the upper vertex and the side which has width w of y. And this whole triangle over here is going to be proportional to our large initial triangle. So it means that we can compute w of y from the similarity relation in that triangle. Apologies if I'm making it too simple. So, over here, we got w of y divided by the width of the side of the bottom of 2. This one is going to equal the width, the length of this side divided by the total length of the vertical side of the triangle. So it's going to be y divided by 2. Good? Okay, so this means that the width is just going to be 2y divided by 3. So we can go back to our computation over there and write our newly discovered fact. On the strip is rho gy times 2y over 3 times delta y, which gives rho g y squared 2 over 3, I can just put in front, times delta y. Okay, so this is an approximate computation that we do for the strip over here, and it's accurate, assuming that delta y is really, really small, but we would actually like to make it 0. Of course, we cannot, because otherwise this one would be 0. So we first need to total everything in, and then let delta y go to 0. So to compute the total hydrostatic force now, acting on the triangle, we need to add the hydrostatic forces acting on these thin strips. So we just see the triangle being comprised of these thin horizontal strips and add these things together. Now, when we add things together, this makes sense when we have a finite number of objects. So if delta y is like, I don't know, k over n, then there is a sense in which we can understand addition. when delta y goes to 0, we need an infinite number of these strips to cover up the entire triangle, which means that the proper sense of addition, as we learned in calculus B, is integration. So to compute the total hydrostatic force acting on the triangle, we need to write an integral Now, where do I write it? I'll just erase this one. So basically, it's kind of easy to write the integral, having this formula right here. Now, I wasn't very thorough, so I didn't put the measurement unit. I know you all appreciate measurement units over here. As if the formula is not complicated enough. So we just take the number over here. Now this is the function. Delta y is going to form the dy of our new integral. So when we compute the total force, we've got an integral. We just copy 2 over 3 rho g y squared. And delta y is going to form the dy of v. Okay? And I will explain a little bit more on the formula right now. But this is exactly how the integral is formed. And I need some bounds of integration. Now, what is y supposed to measure? Y is just supposed to measure the depth. Everything is expressed as a function of the depth, which means that if we were to put some bounds on the depth, we would have to make y range between 0, because the upper vertex is exactly at the top of the surface of the water, and y needs to go down all the way to the bottom of the object, which is submerged underwater. So it needs to go 3 meters underwater. So if I were to put coordinates over here, I would just say from 0 to 3. So just to convince you a little bit that this is a proper way of doing the summation, let me just point out that this would require an intermediate step, like passing through a Riemann sum and then just taking the limit of Riemann sums to form the appropriate integral. So if you just imagine that delta y is something consistent, like perhaps 3 over n or something, so if you like take, let's say, capital N little strips over there, and you would add those things together, you would write the summation perhaps of this sort. Delta y would be something like 3 over n, and you would take 2 over 3 rho g y k squared times delta y. And then you take the limit over here, either as delta y goes to 0, or equivalently as capital N goes to infinity. And you know what this is. You know that this is a Riemann sum of a corresponding function, and the corresponding function is just this one over here. Okay? So I'm not really stressing on the Riemann sum, because in practice we just go straight from the formula over here to the corresponding integral, because the transition is like a one-step transition. We just replace the delta y by dy. So it doesn't really make sense to complicate ourselves by writing the Riemann sum. Nonetheless, it's good to keep in mind that the complete picture is that we have a finite summation, and as we let delta y go to 0, this is a limit of Riemann sums, and it's going to converge to an appropriate integral of a well-defined function. Okay, so this is like a side comment. Which means that you don't really need to write this. And you are free to forget it, as soon as you do. Now, let's compute the integral right here. So that's cycloid for the side. Let's compute the integral right here. Now, if you've kept rho and g unchanged, if you haven't replaced them by their exact combinations, now you get to factor them outside the integral sign because they're constants. They don't change with depth. So I can just write over here 2 over 3 rho g times integral between 0 and 3 of my squared. And you notice that the integral right here is not very complicated. And in fact, most integrals that come from computing hydrostatic force or pressure are not more complicated than this one. They're just quadratic polynomials, integrals of the form y squared plus 4y, something like that. So if you know the process, computing the integral is not going to cause any problems. So let's do it. 2 over 3 rho g times y cubed over 3, integrated between evaluated f3 and 0. Now, this is 27 over 3, it's 9. I can cancel 9 with the 3 factor over here, and I get 6 rho g. And the measurement unit is in. And now I've got to turn it into an exact computation. The exact computation, the density of the water is 1,000. The constant of gravitational acceleration is 9.8. So I've got 6 times 1,000 times 9.8. And I get something which is 58,000. Okay, so let's review a little bit what we did over here before we move over to the next example. So we had an object which was submerged vertically underwater, which means that the pressure is not constant along the object. We chose a vertical coordinate y, which just measures the depth from the top of the surface. And that enables us to compute two important quantities, the hydrostatic pressure and the hydrostatic force. Now, the hydrostatic pressure only depends on the depth y. So to compute the pressure, which is a computation that I've erased to make space for the Riemann sum, which I now deeply regret, but the pressure was just rho g1. That was the point. So the pressure is something that you can compute straight ahead by doing that computation. And then to approximate the hydrostatic force on the side of the triangle, what I need to do is just to approximate the triangle by thin strips, which sit roughly, well, all points on the strip sit roughly at the same depth underwater. So this is an example of such a strip. It has width W of y, which depends on y, height delta y, same for all strips. Now, on this strip, points sit roughly at the same depth. Delta y is assumed to be very small. So to compute the hydrostatic force, we get to use the formula which says hydrostatic force is simply pressure times area. Okay, but what was the area? The area was just W of y delta y. So in this way, we were able to approximate the hydrostatic force on the level over here. The only tricky business was to compute the quantity W of y, to compute the horizontal length of the strip. But this is a combination that once you do an example or two, it's just going to become automatic. You've got two similar triangles, their sides are proportional, the horizontal length can be computed from the similar relation. In our case, it was 2y over 2. So the hydrostatic force acting on the strip was just the pressure at depth y times the area of the strip. This is 2r over 3 delta y. This is how it looks like, but this is just on the strip. And now to compute the total hydrostatic force, we need to add them together. Because we are adding an infinite number of strips and delta y goes to 0, the appropriate addition is just the integral. This is the integral of exactly the function from before. Delta y becomes the dy of the integral, and the appropriate bounds of integration are just basically measuring how far your object stretches in terms of the y-coordinate, in terms of the depth. And it goes from the top of the water, in this case, where the upper vertex of the triangle sits, all the way to the bottom, that is at depth. So we've got an integral over here that we can evaluate. As I said, integrals that involve hydrostatic pressure, force, they're not more complicated than this. Okay, so any questions about this example? Okay, so let's vary it by just a bit. So let's consider the same triangle, but let's submerge it a little bit deeper underwater. So instead of putting the upper vertex of the triangle at the surface of the water, we're gonna put it, we're gonna submerge it 4 meters below the level of the water. So let's consider the new picture then. And let's see what changes. So this is the surface of the water. This is the triangle. My own triangle is submerged deeper out the water. 3 meters here, 2 meters here. And from the surface of the water here, 4 meters. It's not exactly very proportional with what I'm writing, but you can envision the picture. And we've got the same question, what is the hydrostatic force acting on one side of the triangle? So this is what we're saying. Okay, so now we've got some choices. So we want to apply the same strategy as before. In other words, we want to think of our triangle as being comprised of thin horizontal strips where the pressure coming from the water is roughly constant, and we want to compute first the hydrostatic force acting on that thin strip. So we haven't really changed our strategy, but something does change because our triangle is now submerged further underwater, so our intuition says that the pressure coming from the water has increased comparative to the previous example. So now we have two choices. We are going to denote by y something. That something could be the depth as before, so we could let y just measure the distance from the surface of the water, or we could let y measure the distance from the top of the triangle. Because now top of the triangle doesn't sit at the surface of the water anymore. So we've got two possible choices in how to label our picture over here. And these choices are obviously going to lead to the same final answer, but the intermediate computations are going to be a little bit different. So now, if you choose to let y denote the distance from the vertex, from the upper vertex of the triangle, you will get to keep most of the computations from the previous problem, like you will get to keep the computation for the side w of y over here, because you are measuring the triangle in the same way. Y is going to be the distance from the upper vertex to w of y. So basically the measurements of the triangle are going to be the same. But what is going to change is the pressure P of y, because y would no longer be the depth. So if you were to use the formula rho g y, you would need to say something like rho g times y plus 4, because you are going 4 meters down. So this is the picture if you choose to let y denote the distance from the upper vertex of the triangle. Now, if you choose to let y denote the depth, just as before, you will get to keep the formula for the pressure, because the pressure depends on the depth. Y is the depth, so this is the formula. But the measurements on the triangle are going to be a little bit different now, because the relation between w of y and y is no longer going to be quite the same. So let's, for the moment, choose y to denote the depth, just as before, and see a little bit how the computations change. So let me give some parts of the previous example on the board. I'll just keep the formula over here and erase the rest. So this is from the previous exercise. I keep it over here, and I'm going to write around it. So, as before, the first thing that we can write is the formula for the hydrostatic pressure at depth y. And this one is going to be P of y equal to rho g1. Just as before. Okay, so now we do the same business. We take some thin strip at width y. So this is y from here to here. This is y. And at level y, you have a thin strip of width wy and height delta y. And let's try to estimate the total hydrostatic force acting on the strip. So we've got hydrostatic force acting on a thin strip as before. The thin strip is located at depth y with w of y and height delta y. So the area of the strip is going to be as before. It's going to be w of y times delta y. So the only thing that changes now is the width w of y, because you see the triangle is submerged 4 meters down. Y no longer measures the distance of the side w of y from the top of the triangle. It measures the distance from the surface of the water. So if we were to do similar triangles as before, which we want to do in any case, we have to to divide Wy by 2 on one side, but when we write the proportionality relation, we have to take into account the length of this side from here to here, and divide it by the total length of the triangle. So over here I'm going to write 3, the length of the vertical side of the triangle, but on top I need to put the length of this line segment from here to here. And now this is no longer going to be y, because y is the distance from here all the way to the top. So it's going to be something different. Can you help me? Can you help me figure out what the length of this side is? Y minus 4, exactly. So this one over here is y minus 4, and this is exactly what goes on top. So let me color Chuck. Sorry. Okay, so it means that W of y is just going to be 2 times y minus 4 divided by 3. And we can go back to our thing over here and write the area as 2 times y minus 4 over 3 times the volume. Okay, so the hydrostatic force acting on the thin strip is going to be, as before, the area of the strip times the pressure the pressure hasn't really changed, so it's just rho gy. And for the area, we just plug in whatever we got. So it's 2 times y minus 4 over 3 delta y. So just 2 over 3 rho g times y minus 4 delta y. Can you see on the board, or trying to make an effort? It's probably too late to ask anyway if you can see on the board, so I'll just, for the piece of my mind, I'll just assume that it's seen everything until now. Okay, so this is the hydrostatic force acting on the strip, and now to compute the total hydrostatic force, we need to perform the usual trick and take an integral. Let me write it over here so you know what example it corresponds to. So the total hydrostatic force is going to be an integral. Now I just take the formula right here. I put it as an integrand in the integral, transforming the delta y conveniently into the dy of integration. So it's going to be 2 over 3 rho g times y minus 4 times y dy. And now I need to put some bounds on the integral. So what are the bounds then? Do I put 0 to 3 as before? No, obviously not, because you see the object is no longer at the surface of the water. So what do I put? So what is the proper domain of y? What is y measuring? Y measures the depth, but we only have a hydrostatic force if we are within the area of the object. I mean, we are not computing the hydrostatic force for a point over here in the water. So y is supposed to measure how far the object stretches. I mean, y measures the depth, but the bounds that we put on the integral are supposed to measure how far our object stretches vertically, measured with respect to the y coordinate. So, what is the y coordinate of the upper vertex of the triangle? 4. So, this one goes in the lower bound. And what's the y coordinate of the equals point triangle? 7. So, this is what we put over. Good? Okay, so now again we've got an integral which is not more complicated than the previous one. 2 over 3 times rho times g is a constant that can be factored outside. So 2 over 3 rho g times our integral from 4 to 7 of this function right here, which is y minus 4 times y, and to integrate it, I need to change it into I squared minus 4y d1. And the integral poses no problem as before, so this is just going to be 2 over 3 rho g times y cubed over 3 minus 4y squared, so minus 2y squared. Evaluated between 7 and 7. And let me throw in some computations over here so we don't lose time. So after you evaluate it, you get something like 1076, 400. So you get some computation. How do you compute it? Well, rho you replace by 1000. G replaced by, so this is 1000, this is 9.8, and you know how to evaluate that function at the lower and upper bound. I know I'm cheating a little bit with the advantage of having some notes, and you're not going to test me whether this is correct or not anyway, so if you discover a mistake, you'll discover it well after the class is over. I don't want to challenge you, so go into the conversation. In any case, you see that the hydrostatic force has increased from the previous example, as it is normal because we submerged the object deeper underwater, so naturally the force has increased. Okay, so this is the computation that takes into account just the coordinate y, which measures the distance, which measures the depth, which measures the distance from the top of the water. Now, this is the final computation, but for our exercise, let's see what would have happened if we chose to denote by y the distance from the upper vertex of the triangle. So, let's do a tiny bit of exercise over here. And let's see what changes if instead of letting y measure the depth, we let y measure the distance from the upper vertex of the triangle. So let me do it somewhere on a corner, like perhaps here. This is the triangle, and now y measures the distance from the upper vertex. So this is y. This is capital Y. This is delta Y, as before. And the distance of the surface is 4. From here to here is 4. The total side of the triangle is 3. And the horizontal side is 2. So suppose we do that. Now, what changes? I just want to show you that we get the same integral but translated. So via substitution we actually get the same integral, so it doesn't really matter how you choose to denote things. So what changes over there? Y denotes the distance of the level W of Y from the upper side of the triangle. Okay, but this is then exactly the same picture that we had in example number 2. So it means that when we compute W of Y, we get to use the same proportionality relation from that triangle. So it means that when you do it over here, and when you compute the area, you get to use a formula which is W of Y delta Y. But W of Y is the same as the W of Y we got over here. It's W of Y over 2 equal to Y divided by 3. So this is just going to be the same as in the previous example. In the first example, it's going to be 2y over 3 times delta y. So this is as in example 1, as in an example with the triangle sitting at the top of the water. But when we compute the force, we are going to see a tiny change right here. Because if we choose to let y denote the distance from the vertex, and if we want to compute the hydrostatic pressure at level y, then you know the hydrostatic pressure depends on the depth. It doesn't depend on the distance from a random point. So if we want to compute the hydrostatic pressure at depth y, we've got to add to y 4 meters extra. So in here, I'm just going to change it by saying Q of y is going to be rho g times y plus 4. Natural? It's just because if y is the distance from this point to the top of the triangle, then the total distance to the surface of the water is y plus 4. Good? Okay, so it means that when you write the integral, the corresponding integral, you are going to get something like integral of rho g times y plus 4 times the area right there, which is 2y over 3 1. And now, what bounds would I put on the integral? Well, you see, in this example, y measures the distance of this point from the upper vertex, which means that y is going to range along the vertical length of the object. So if you are at the upper vertex of the triangle, it means that y is 0. If you are at the bottom of the triangle, it means that y is equal to 3. So you would end up with an integral between 0 and 3. And you notice the connection between these two integrals. So this is an integral of, just compare this one to the one in yellow. That's an integral between 0 and 3 of rho g times y plus 4 times 2y over 3. And this is an integral between 4 to 7 of 2 over 3 rho g times y minus 4 times y. So you should straightforward see the connection in terms of substitutions. So you should see that if we choose to do a substitution, let's say over here, and let u denote y plus y minus 4, then we would immediately get the other one. So if I use this integral, I do the substitution equals y minus 4. du is going to be dy. And you see that we immediately get out. Okay, guys. So in practice, in here it makes sense to compare because we have a triangle which submerges further and so on. But in practice, if you want to make your computation easy, you let y denote the distance from the surface of the water because it helps you immediately calculate the hydrostatic pressure with no further complications. So you let y denote the distance from the surface of the water, compute the pressure, and then approximate the force using the process here, and combine everything.